How do you know when to add pKa's? How do you know when to add pKa's like this? The pH is equal to the pKa plus pKa divided by 2. That one? Yeah, that equation you have to memorize when to use that equation. And so when do you use that equation? That equation is only used when you have what? Not dicritic. This equation is used only when you have a amphoteric. And so how do you know when to use it? When you have an amphoteric species. So on one of the tests I gave this species, 0.100 molar sodium monohydrogen phosphate. Monohydrogen phosphate is amphoteric. Monohydrogen phosphate can hydrolyze water as an acid or as a base. In fact, it does both. You can't stop one or the other. And so it's amphoteric. Therefore, when we have an amphoteric species, we have to solve Ka and Kb and Kw simultaneously. But solving 3 equilibria simultaneously isn't so easy. But it turns out it's easier than normal because the Ka and the Kb have the exact same reactant, that is monohydrogen phosphate. We didn't do this, but there's a lot of work, and they came out with this simple equation, which is like an engineering equation. You just memorize it and plug and chug. But that's only valid for amphoterics. Some amphoteric species we ignore one of the values. For example, hydroxide. Hydroxide is amphoteric because hydroxide can lose a proton to form oxide or can gain a proton to form water. And so hydroxide is amphoteric. And so it might act as an acid or might act as a base. But when we compare the Ka for hydroxide versus the Kb is very large. The Ka is very, very small. It's negligible. In fact, if we wanted to calculate the Ka for hydroxide is equal to Kw divided by the Kb for its conjugate base. What's the conjugate base of hydroxide, the acid? Well, if hydroxide is the acid, the conjugate base would be oxide. And what is Kb for oxide? Very large. And so this is very large. This is going to come out very small. And so sometimes we'll just ignore this and just treat hydroxide as a base, right? And so there's an exception where, yes, that's amphoteric, but the acid is so weak, we really don't consider hydroxide as being acidic. You know? Whereas something like monohydrogen phosphate can go either way. Okay, if you take a look at this reaction, you can see iodine's coming off. Right off the electrode, it's purple, and then as it gets diluted, it turns a lighter shade or brown color here. Over here, there's bubbles of hydrogen gas forming. There's also hydroxide that's formed here. And so if I add a drop of phenolphthalein, then we can see the hydroxide that's being formed here. So let me add a drop of phenolphthalein. You see all the hydroxide at the electrode. All right, other questions? All right. There's different ways of looking at that particular problem. And so let's take a look at one way of looking at it. What is this What is E for this one? Is this a reduction or oxidation? Reduction. What is the reduction potential for this? Do you know? It's 0. This is 0 volts. How do you know? It's the standard. So anyway, H plus, does that mean it has 0 oxidizing ability? And so if I had 1 molar H plus, here's an electrode, and consider the electrode like a sea of electrons. There's a whole bunch of electrons in metal. If I stick this electrode, the cathode, in a beaker, and this beaker contains 1 molar H plus, does that 1 molar H plus have no pull on the electrons? I know it wants 2 electrons, but it's got 0 volts. It wants 2 electrons, but it's got 0 volts, so it's got no pull. Is that correct? True or false? That's false, because we know H plus is a decent oxidizing agent, right? So if H plus is a decent oxidizing agent, then this 0 is just some arbitrary 0, right? And so the way to think about this problem is like this. Okay, if I have 1 molar, then the pull is 0 volts, which is something, 0 volts. It's like 0 C. If the temperature is 0 degrees C, does that mean it has 0 temperature? No. Well, what is the temperature? The temperature is 0 degrees C, but it does have temperature, right? Well, the same thing. Well, this has 0 volts, but it does have some pulling power. It's a decent oxidizer. Now, what happens if I make this 2 molar rather than 1 molar? H plus. If I make this 2 molar rather than 1 molar, is the pulling power the same? 0 volts? Is the pulling power greater than 0 volts? Or is the pulling power weaker? The pulling power should be stronger, which means the voltage should be greater or higher. And so there's going to be a greater voltage on the electrons being pulled to this electrode, having 2 molar instead of 1 molar. Everything else is the same, so we'll ignore everything else and just look at this, right? And so to answer this particular problem, you would have to know what the standard is. The standard is 0 volts, under standard conditions. And then compare it. Okay, other questions? Yeah. So take your time. Fe3 plus, Fe2 plus, H2O, and Na plus, or none. Well, let's do water. I know the Ka for water. The Ka for water is just equal to Kw. How do I know that? How do I know that is because the Kw is water plus water. And so we think of this as acid. Acid plus water gives us hydronium, and in this case, hydroxide. And so Kw is unique because Kw is Ka and Kw is Kb. But anyway, does water have a very big Ka? Is water very acidic? It's not that acidic because if we think about the polarity of this bond, it's quite polar. This is a very polar bond, but perhaps not polar enough to make water a strong acid. And that's the case. You'd have to know something about Fe3+. Fe3+, how can Fe3+ be an acid? There are no H pluses to donate, you know? Acids are H plus donors in the Bronsted sense. And so this is what you'd have to know about Fe3+. And actually, let me show you. You'd have to recognize Fe3+ can be a Bronsted acid. It's not the Fe3+, but when Fe3+ is water, it forms a hexaaqua complex. And the hexaaqua complex is actually more acidic than HNO2, more acidic than HF, more acidic than formic acid, more acidic than acetic acid. And so it's actually quite acidic. It's less acidic than phosphoric acid, but it's right next to phosphoric acid. And so you'd have to know that, the Fe3+. Turn it off. And so what this is it's actually the hexaaqua iron 3 ion. And it turns out that hexaaqua iron 3, what happens when the water becomes a ligand? When the water becomes a ligand, it's going to bond directly to the iron 3. So we got the iron 3 here. Now we attach a water here. Iron 3, and there's going to be an inductive effect. And so iron 3 is quite electron poor, which sucks electron density away from oxygen, which in turn sucks it away from hydrogen. And so when we look at the delta plus on a water molecule bonded to an iron 3 versus a free water molecule, then this is going to be a heck of a lot more polar and more acidic. And that's because of the inductive effect. We have a 3+ charge, which is electron poor, sucking electron density away from the hydrogen. So we should be able to do these two. Which aqua complex will be more acidic? Iron 2 or iron 3? Iron 3, because iron 3 is going to have a greater charge. Rather than a 3+, if I only have a 2+, I'm not going to get as strong of an electron withdrawing effect. I'm not going to get as strong of an inductive effect. And so the delta plus is going to be smaller than the delta plus for iron 3. Sodium ions are just +1. It's nothing significant. Sodium doesn't really form an aqua complex because it's charged. It's not a very good Lewis acid. And so the answer would be, which one has the biggest Ka? Iron 3. Uh-huh.
So it's also the more acidic one.
Yes. It would be the more acidic one. Yes. All right, this has been going for a while. A lot of bubbles of hydrogen gas are forming over here. But what I'm going to do is, I'm going to do this. Rather than electrolyze potassium iodide, I'm just going to electrolyze water. And so I'm going to take these electrodes off here. Over here, you know, I'm sucking electrons into the power supply. I was oxidizing the iodide. But now I'm going to just put this over here. These are graphite electrodes. They're platinum electrodes inside here. And so I'm going to suck electrons away from water. When I suck electrons away from water, I oxidize water, which forms O2 gas. And I'm going to force electrons into water and reduce it. When I reduce water, I form hydrogen gas. And so over here, I should form oxygen gas. Over here, I should form hydrogen gas. So let's flip this on. Let's crank up the voltage. Take it like 9 volts or so. And 9.67 volts. So bubbles of gas are forming already. There. You could electrolyze water with a 9-volt battery. Okay. Other questions? Uh-huh.
In exam, question 6, there's 6 moles of sodium hydroxide versus 80
All right.
Wait, chapter 17?
60.
All right, so 6 molar sodium hydroxide is going to have 6 molar hydroxide. Sodium salts are all soluble. Soluble salts are strong electrolytes, so we expect to find 6 molar hydroxide. If I have 6 molar hydroxide, there's another source of hydroxide, and that's water, Kw. Should I worry about Kw?
It's negligible.
It's negligible, right, so I'm not going to worry about it. And
It's
so
like 6 molar coming from sodium hydroxide.
right, and so let's look at the power of the hydroxide ion concentration, would be the negative log of the hydroxide concentration. It would be the negative log of 6, which comes out to what?
15 point something.
Not the pOH.
Like about
No, the pOH should come out negative.
Negative 0.77815.
I meant the pH.
Yeah, right. And so we know that the pH, sorry,
Lesser.
plus the pOH is equal to 14.00. And so the pH is equal to 14.00 minus the pOH. There's a lot of people, what they did was they got to screw it up here. Because a minus is a plus, so the pH comes out to 14.778.
Which is about 15.
Which is, yeah.
The pH is going to turn dark red.
Yeah, that is a trick question. Because normally you would think to subtract it.
No, I mean the pH fading. It turns dark red at 15. It's going to be super duper red.
Okay, other questions?
Anyone look at chapter 7? That question's in there.
CuCN at pH 4.3, what was it? pH 3.
Oh yeah, I was struggling with that one.
Is 3.2 percent to the minus
KSP, the number sign
Is it like the proton and the hydroxide going to water, like they combine the two equations?
and 6.2 times 10 to the minus 10.
Well, whatever we have solubility in pH, we need KSPA, right?
Wait, why is that?
Well, let's take a look. The KSP equation we could write out. The solid.
What's the difference between KSPA and KSP?
Well, KSPA is going to have a way where we can figure out the H plus or the H3O plus. If we look at the KSP here, there's no direct impact on, how does pH impact this? Well, cyanide is a pretty good base. And so we know pH is going to impact this because there's cyanide there as a base. But how does it do so directly? Well, it's hard to tell. And just looking at the KSP equation, where do I plug in pH 3? In this equation, where would I plug in pH 3?
The cyanide hydrolysis is in the water to form hydronium and HCN.
You could do that. You could do that and then add those two up, but there's a problem with that.
You times the negative 3 to get the molar.
Yeah. So this is means that the H plus or hydronium ion concentration is equal to 1.0 times 10 to the minus 3 molar. And so where should I plug that in? I can't plug it in here. And so I don't want to do this. I don't want to do this. Base plus water. Base plus water is called Kb, right?
It makes hydronium. Certain it?
No. This makes HCN plus.
No, add it to hydrogen.
So we don't want this. We want to see how the hydronium is going to impact this directly. So we look, acid's going to attack any bases around. The base that's going to be around would be cyanide. So H3O plus cyanide gives us HCN plus water. If you look at this equation, going backwards, it's acid plus water gives us hydronium and conjugate base. So acid plus water. And so that's a Ka equation. So this is 1 over Ka for HCN. This is the KSP. If we add up these two equations, then we can see directly how the solubility is going to be impacted by hydronium ion concentration.
Oh. Well, why can't we do KB? Why can't we? I do not forget this concept, but I just want to wonder why. So that I won't do that on the test.
You could use Kb. You could use KB. Hmm?
KSCP, you just know such a thing. But not KSCP.
The problem is this. This method is called the stepwise method, the simultaneous method, or the combined method.
Combined.
In the combined method, what do we want? We want step 1 to be very small and step 2 very large. If we use KB, can we use the combined method? If we use KB, can we use the combined method?
Finding what's the KB for this?
The KB is going to be KW over KA. KW is 10 to the minus 14 divided by 10 to the minus 10 gives us about 10 to the minus 4, roughly.
That's large though, right?
Not really. Not really. And so you wouldn't use the combined method if you use KB. You would have to use the simultaneous method most likely.
Which will make our life harder.
Right, right. Which
Yes.
will,
KSP plus KA equals to KSPA.
Yeah, this will make your life much easier if you just use KSPA. And then we got to figure out, is this pH at equilibrium or is that pH initial? And so how was the question phrased again?
What is the solubility of copper cyanide at pH equal to 3?
Okay, then what is the solubility at pH equal to 3 means that this has got to be equilibrium. At equilibrium, it's got to be 1.0 times 10 minus 3 molar because that would give us a pH 3. And so what they want to know is what is the solubility? Well, solubility is going to be, well, this is 0, this is 0, this is 0. That means we had some initial amount here, which we don't even care how much was in the initial. And then there's going to be minus S molar, plus S molar, plus S molar. Actually, water is pure liquid, so ignore that. And so at equilibrium, we're going to get S molar and S molar. And so we solve for S. And so this is going to be equal to the Cu plus concentration times the HCN concentration divided by the hydronium ion concentration. Everything is to the first power. The coefficients are all 1. And so this is going to be S squared over 1.0 times 10 to the minus 3. And then we solve for S. Kelly.
In what way would you word the question if you want the initial pH?
I would say something like this, you know. I would say something like, what is the pH not, what is the solubility, what is the solubility at pH 3 means that it's got to be pH 3 at equilibrium. But I might ask something like, what is the solubility of copper cyanide, copper 1 cyanide, in a solution, well, in a pH 3 solution, in a pH 3 solution, rather than at pH 3.
In the pH 3.
Yeah.
So why does that mean initial? Because the solution was at pH 3?
Initially, yeah. And then you're adding the CuCN to that. Or I'd say, you know, to make it clearer, I would probably say, what is the solubility of CuCN in a solution, maybe initially at pH 3?
No, that makes it clearer.
Okay. Let's say something like that.
Got it. That's really important.
All right. What's next? Does that answer the question, or should I finish it? Okay. Yeah, just solve for S, and that should be the solubility. Okay, other questions?
Oh yeah, that was
yeah.
at the pH of the solution of HNO2 and like something. Does everybody have to take
Sam, someone asked a question right now. For chapter 17, show how the pH is calculated for a mix of 10 milliliters of 0.10 molar HNO2 and 10 milliliters of 0.10 molar NH3 with the, you gave us a KV value and then
Yes, thank you. I struggled with the question. It's a good thing you're joined. Huh?
You need it? You want to see it or no?
I could borrow it only for a while. I'm leaving in 7 minutes, but
HNO2 plus NH3
yeah.
is going to yield what? So what is K equal to here?
What do you mean? asking for, he gave
us PK.
pKa and then Kb for NH3.
Could we figure out what K is for this equation?
We could do the, I was gonna do the,
Yeah, except we don't know the concentrations.
can you just use the power of the negative pKa?
No, we have to add up equations. So this is like a Hess's law type problem. And so we'll try to get this. This is going to be our net reaction. And so one thing we might try to do is take HNO2 plus water. HNO2 plus water, this is called the Ka or pKa reaction for HNO2. This is going to yield hydronium plus nitrite.
Excuse me, does it form ammonium nitrate and water? Where's the water? And the first equation, where's the water?
There's no water.
How do you know that HNO2 and NH3 together make that?
Make this up here?
Yes,
Was that given or that wasn't given?
we gotta predict the products.
Okay, how do I know? Because you always react the strongest acid with the strongest base.
So that was the Bronsted-Lowry.
Right, and so what is the strongest acid? Water,
HNO2.
HNO2, or NH3?
HNO2.
Yeah. And then you could see what forms, because the strongest acid will lose a hydrogen to the strongest base present. The strongest base present would be ammonia or water or HNO2.
Ammonia.
Yes. And so this is how we get those reactants here. If we look at Kb, that's it. Let's add these two up. The second equation is Kb for ammonia. Do you recognize it? And so we get HNO2 plus NH3 plus 2 waters yields H3O plus NO2 minus plus NH4 plus OH minus.
Wow. Why do we have to add it?
Trying to figure it out. Then if we do this, if we take an H3O plus an OH minus, this is going to give us 2 H2O liquids. This is 1 over KW. And then add that.
Adding more equations?
And this is going to give us HNO2 plus NH3 yield H3O plus NO2 minus plus, oh actually H3O plus cancels. Do you see H3O plus cancels? So we're just left with NO2 minus plus NH4 plus.
Which we end up up there.
Yeah, right, this is the equation we want, right? And so if we couldn't use the combined method, we just add up these.
But excuse me, if we know right away it's a Bronsted-Lowry, do we have to do all of this?
How are you going to figure out K without doing all of this?
Wait, we're not done. We're not done with running yet.
So what do we do? Well, now we could do the ice table, right? So we do the ice table.
But the question is asking for the pH, not K, right?
We need K to do the ice table. And it turns out that K is not so big, so we're going to get a concentration of HNO2 at equilibrium after we do this. We're going to get some NH3. It's not a complete reaction. There's going to be some leftover HNO2 and NH3. And then we're going to produce some products, NO2 minus, and then some NH4 plus. So we'll get some concentrations here. Okay, after we do this ice table, we get K, we do this ice table, we get those equilibrium concentrations, and then what? Oh, well, K's already solved, because K we're going to solve here by multiplying these K's. So we know what K is. Well, then we know that, what was the concentration here, 0.1? This is 0.1. This is 0. This is 0. And then we solve for x. This is minus x, plus x, plus x. We solve for x, and then we solve for the equilibrium concentration. We can calculate the equilibrium concentrations there. But the problem is what do we do next?
So are you telling me that this is not the way to solve it?
Yes.
So then we're stuck here.
Well, we're going to be stuck because next thing we'll say is, okay, we have acid, base acid present at equilibrium. And so how do you handle a solution like this? Well, here we could do the Ka for HNO2. That's going to contribute hydronium. But then there's NH4 plus also. So we'd have to do the Ka for this. That's going to produce hydronium. But then there's water. Water is also going to produce hydronium. So we're going to have 3 hydronium producers. And then we look at Kb, you know, we have 2 bases plus water. We're going to have 3 hydroxide contributors. And so pretty soon this is going to be quite a mess. And so even before I would have gotten to this point, if you would have just said that, you know, weak acid, weak base mixture has to be solved simultaneously, you'd have been okay. And so basically this has to be solved simultaneously because we're going to have some trouble coming up soon. Right. And so how do you do this? You have to solve it simultaneously.
Weak acid, weak base equals simultaneous.
Right. But it depends on how weak and how strong, because in the book sometimes they don't do it simultaneous. You know? Like I think with acetic acid they didn't do it simultaneous. All right, other questions?
Oh,
Uh-huh.
so would you incorporate this into the final because then it's multiple choice?
Would I incorporate it into the final?
Yeah, like how is that going to work? This would take longer than 3 minutes. Yeah.
If this takes longer than 3 minutes, then I would compensate with other problems that would take a lot less than 3 minutes.
So you'll ask us.
How would I incorporate this into the final? I would see if you just have general knowledge. So I'd say, you know, you're titrating nitrous acid with ammonia.
Okay.
How would you solve for pH? Stepwise? Combine? Or simultaneous?
Wait, can you go over when you use the combine his first step has to be small, KA,
The first K has to be small, the second K has to be big. Yeah.
What do you mean by small? Like your KA needs to be small, which is
Like whatever, like KSP, you know, KSPs are small in general. And your second step would have to be big, and your second step would be like in a KSPA, would just be the reverse of a KA, you know, 1 over KA.
the stepwise.
Stepwise, most problems can be solved stepwise. Combined method you use for things like KSPF and KSPA.
And what's the last one?
Last one?
Combine into a stepwise.
Oh, simultaneous, yeah.
What's the difference between solving it stepwise and then solving it simultaneously?
Solving it simultaneously would give you a better answer, more accurate answer, because stepwise you assume that there's no perturbation, but not to, well, it might not go to completion, but you assume that whatever the next step is very small compared to the previous step.
So can you use simultaneous method for everything then?
Yes.
Mostly?
Simultaneous is the general method for everything, but it's too much work to do everything simultaneously. This is why you look for shortcuts where you don't have to do simultaneous. But simultaneous will work for everything. Simultaneous is how Visual Mintex solves problems. It solves all the equilibria simultaneously. But if you start running into a large number of equilibria, then it's going to be too much calculation to handle by hand. You would want to do it on a computer. Does that answer your question enough? Or
Yeah.
all right, other questions?
For the reactions,
Uh-huh.
there was one that said iron to chloride and potassium iodine and HCl.
What was it?
Potassium
Iodate
that's what it says.
and HCl?
Yeah.
What kind of reaction is that looking like? Oh, yes. Yeah. Well, if you were to guess, what kind of reaction is that? P at acid base, yeah. You know, we have a proton donor, HCl. Which would be the proton acceptor? Well, it could be this. If this were the proton donor and this were the proton acceptor, then we'd form HCl from HCl. So over here, if HCl is the proton donor and the potassium iodate is the proton acceptor, then we see there's a difference here. Iodate might react with that proton in HCl. And so if we were to inventory this, we say iodate plus the H plus from HCl react to form HiO3. What acid is HiO3? Well, if the anion ends in 8, then we use the ic acid ending. So this would be iodic acid. H plus and IO3 minus. HIO3 is iodic acid. So, this is possible, except is there a driving force for this? What's the driving force for Bronsted reactions? Yeah, and so here's our stronger acid. Is HIO3 a weaker acid?
Strong.
Yes. So this is strong to strong. Is a strong acid to a strong acid a driving force? No. And so we have no reaction here. And so no Bronsted acid base. What else would you try?
We don't have to do.
Yeah, you could try metathesis, but metathesis will get nothing here. No precipitate, no gas formation. And then we try redox. And so redox, you inventory it, pick the strongest oxidizer, pick the strongest reducer, and react those together. Determine if there's a driving force. And it turns out there is a driving force for this. Do you want to try it? Do you want to try to pick it out or move on?
Try it.
All right, why don't you try it and see?